All right, so what do these waves mean? What is this like? Okay, what we know they exist on the heart monitor, but how do you generate those? What do they mean? So then here we have the atria and they're depolarizing. Again, you're going from the SA node to the AV node. So as these conducting cells depolarize, they tell those muscle cells in the heart walls to contract. So this is what we have, why you have atrial systole. But that depolarization, that also, again, you have ions moving, you have initially you have all that sodium rushing in. So that's electrical, that movement of ion is actually a detectable electrical current. It's not going to like shock someone if you touch their heart with your hand. You're not going to be able to feel it through your skin, but it is a slight electrical current that can be detected by electronics. So the depolarization of all of these atrial muscle cells, this causes the slight bump you see in the P wave. So this is due to the depolarization of atrial cardiomyocytes during their action potentials. So it's this increase in the membrane potential of all the cells here in the atria causing this P wave. So that's why the P wave corresponds to atrial depolarization, that uptick in the membrane potential. And that's why we covered membrane potential. Again, if you're going back on this and you're like, what's membrane potential? Go back to membrane potential because, again, it's hard to really understand this unless you understand potential and depolarization. Now, what we have here is that now the conducting system is propagating action potentials and passing it along. So again, the whole purpose of the conduction system is to kind of coordinate things. You want the atria to contract before the ventricles. So this is why it proceeds in a wave-like pattern from the SA node down to the rest of the conducting system. Now we're at the AV node. Now we're trying to spread it through the bundle of His and bundle branches. And now this signal is going to go along the ventricles and then to the Purkinje fibers. So as it does that, it's going to tell all the cardiomyocytes in the ventricles to fire off and contract. So now you want to stimulate ventricular contraction. And this is what causes the QRS complex. Part of the reason you have that slight dip is due to the atria are actually trying to repolarize during this time, but for now, notice what I want you to know is like, okay, we have this R wave, and it's very important, especially in diagnosing many of these, to kind of look at the R wave. And what do you also notice about the R wave? Look at it compared to the P wave. Notice that the R wave is much, much taller. It has a higher amplitude than the P wave. So what's causing the R wave is due to all the action potentials in these ventricular cardiomyocytes. And again, those ventricular action potentials go back to our action potentials lectures from last time. So from all of these cells having a jump in their membrane potential toward the positive, that causes that strong positive deflection in the R wave. And why is it bigger than the P wave? Well, which has more muscle, the atria or the ventricles? Collectively, the ventricles have many more cardiomyocytes than the atria. This is why the R wave is bigger in height and amplitude than the P wave. So the R wave is due to ventricular depolarization. Now, then we go back to, so the thing is that now you have to reset it. Remember, it's a cardiac cycle. So we had the atria contracting and doing atrial systole. We had the ventricles contracting, doing ventricular systole. You have to reset the whole thing again. And remember, all these action potentials, they jump up in the membrane potential, but they're brought back down eventually. So this is what we call repolarization. And the funny thing is that, okay, if you have the opposite type of membrane potential change, it should deflect toward the bottom, but so toward the negative side. And so this is what we would see if if repolarization was going this way. Now, this is where having labs online is kind of like tough having our physiology class online. Because what happens if the EKG tech switches the leads? Like they put, instead of having the positive down here and the negative up here, they somehow switch the two. Well, if that happened, the funny thing is that that would actually cause the whole EKG printout to be flipped upside down. So I know this is one of the big humps in this thing. So if this was going toward this negative repolarization was going this direction, it would downwards deflect like this. But actually this negative repolarization goes in the opposite direction of this EKG leg. So this is, I know it's very confusing, but this is the way I think of it. It's kind of a double negative. Repolarization goes toward the negative, but now you're going to the opposite direction of depolarization. So what that does is ends up flipping up the T wave and this deflection in the ECG toward the positive. So yeah, I know it's one of the things you just have to kind of it's confusing at first, but when you accept it, it gets a lot easier. And the way I think of it is it's a double negative. You have repolarization toward the negative, and it's also going toward the negative side of the electrodes. That's why the T wave, instead of dipping down, it actually deflects upwards. So two things you should get away from, or two things you should take away from this. The T wave is not causing contraction. It's actually everything resetting in the ventricles. And the other thing is it's caused by this drop in membrane potential at this phase of the action potential in the ventricular cardiomyocytes. I know, if you got it, great. If you didn't, don't worry, or just ask me again during office hours or during the review session. So it's just one of those, it's just like action potentials. It's just one of those things you just kind of have to sit down and explain it best in your own mind until it sticks. And it does trace to, so the whole thing about the EKG cycle, this is why the EK or ECG, I know I use them interchangeably. This is why ECG waves repeat over and over again. Your cardiac cycle repeats, therefore, and you have atria contracting, you have the ventricles contracting, and they both relax. So this is why the ECG repeats over and over again. It's due to the depolarization of the atria, then the depolarization of the ventricles, and then the ventricular repolarization. Okay, so then again, the ECG corresponds to phases of the cardiac cycle. The P wave caused by atrial systole. All those atrial cardiomyocytes, those muscle cells, are depolarizing, firing off their action potentials. That positive membrane potential change causes the little bump. Then you have your QRS complex, and that is triggered by ventricular systole. Again, all those ventricular cardiomyocytes are firing off, thereby causing a bigger bump toward the positive. Again, you have much more ventricular muscle than you have in the walls of the atria. And then the T wave is caused by repolarization and resetting of all the ventricles that are ventricular cardiomyocytes that contracted. And this is what causes, so this is the onset of ventricular diastole. Now all your muscle cells are undoing that previous action potentials and trying to relax.